Okay, continuing on with Unit 5, we're going to discuss dilution problems. So, dilution. You might think, what is dilution? Well, think about orange juice concentrate. You know, the frozen orange juice that you buy in the can. In order to prepare juice from that concentrate, you need to dilute it. So what do you do when you make this orange juice? Well, you just add water, right? 3 cans, is that what it is? Depending on what size of the concentrate you get. So you take the concentrate and you add water or dilute it to make it a tasty concentration, so it's not just overwhelming orange. It turns out that this technique, dilution, is used often. It's much easier to make a very concentrated solution and then just take a little bit of the concentrated solution and add more water to it. This is done frequently to keep costs down. If you have a solution that's less concentrated, you're transporting just water. And so a lot of times very concentrated solutions are made and kept that way as stock solutions, so that all you have to do is take a small amount of it out, add water, and then you have the desired concentration. So to calculate how much something needs to be diluted, this formula is used. C1 or CI VI is equal to CF VF. And so C stands for concentration. The subscript I stands for initial. So this is initial concentration. V stands for volume. Subscript stands for initial, so it's initial volume. So that's your initial concentration, initial volume. That's what you start off with. What's the concentration? What's the volume? After dilution, you have the final concentration and the final volume. So when working with this, the concentrations that you can see are molarity or percent concentrations, the concentration initial, CI, and the final concentration have the same units. Now, with this dilution formula, 3 of the 4 values are given. So we will never give you 2 of the 4 and expect you to find the other 2. So you'll always have 3 of the 4 values given. Remember the orange juice example. Which is more concentrated? The orange juice in the can or the orange juice in the pitcher? The orange juice in the can is more concentrated. So initial concentrations are higher than final concentrations. And that's because we added water to it. So we're increasing the amount of solvent. So now you have less solute. Okay, so let's see what a typical dilution problem would look like. So here is an example of one. 5 milliliters of a 2.5 molar solution is diluted by adding water to make the total volume 25 milliliters. What is the concentration of the new solution? What I recommend when solving these problems is to write a little table. So you can fill in what you know and then put a question mark for what you don't know. So the initial concentration, do we have that? 5 milliliters of a 2.5 molar solution is diluted. So we do have the initial values. These are right here. So the initial concentration is 2.5 molar. The initial volume is 5.0 milliliters. The final concentration, the total 25 milliliters, we don't have the final concentration, but we do have the final volume. So we're solving for the final concentration. So remember, this is our formula, and this is what we're looking for. So to solve, oops, I circled the wrong one. VF. We're solving for CF. So we're solving for the final concentration. So CF, I need to divide by the final volume, so it will be CI VI divided by the final volume. So all I do now is plug those values in. So that table on the left is very handy. So 2.5 molar times 5.0 milliliters divided by 25 milliliters. Your units of volume should cancel and you'll end up with units of concentration. So we have molarity left over, which is good, which is a unit of concentration. So our final concentration is 0.50 molar. Now, just like with everything, we have to pay attention to sig figs. So the most sig figs we can have in this answer is 2. So that's why I have 0.50 molar. Now, the final concentration, since we're dealing with the dilution problem, should be lower than the initial concentration. So you can always double check yourself. Is that true in this case? Our initial concentration was 2.5 molar and our final concentration was 0.5 molar, so that is true. So we had to add water to this to decrease the concentration. So it's a dilution problem. So this is pretty typical of what you'll see for dilution problems. If you look on the next page, there are more dilution problems. So you can pick out a dilution problem from a concentration problem if 3 numbers are given. So 3 numbers is a telltale sign that you're dealing with dilution. So if you look at the next page, you see 3 numbers and number 1, so most likely a dilution problem. Number 2, 3. If you go through these, you'll find that they're all dilution problems. The reason I'm kind of preparing you for concentration and dilution problems together is that on the Unit 5 exam, they will be all mixed together. So it's important to differentiate. A lot of students will try to set up problems as dilution problems, and they're not dilution problems. So I want you to work problems 1 through 4. Hit pause and work those now. All right, so number 1, set up your table. So CI is 3.5 molar, VI is 75 milliliters. We don't know CF and we're looking for, or we don't know CF and we do have the final volume. So we solve for CF. So it's going to be CI VI over VF. So 3.5 molar times 75 milliliters divided by 450 milliliters. Milliliters cancels out. 2 sig figs, so we end up with 0.58 molar. All right, number 2. Again, we're solving for CF. So our initial concentration is 12 molar. Initial volume is 100 milliliters. Final volume, 500 milliliters. So our CF will be CI times VI, or VF. 12 molar times 100 milliliters divided by 500 milliliters. So multiply and divide, and you end up with 3 sig figs, so our answer comes out to be 2.4 molar. Number 3, aqueous ammonia is commercially available at a concentration of 16 molar. How much of the concentrated solution would you use to prepare 500 milliliters of a 1.25 molar solution? So a lot of students have trouble with this one because they're trying to figure out what is the initial concentration. Remember that the initial concentration is always going to be higher than the final concentration because we're diluting, we're adding water. It's not going to be as strong. So the two concentrations we're given in number 3 are 16 molar and 1.25 molar. So definitely 1.25 molar will be the final concentration and 16 molar will be the initial concentration. Now, the initial volume is what we're looking for. The final volume, we know, 500 milliliters. So we solve for VI. It's going to be CF VF over CI. So 1.25 molar times 500 milliliters divided by 16 molar. Molarity cancels out. We end up with milliliters as our units. 3 sig figs, 39.1 milliliters. Okay, number 4. It's another dilution problem. How much water would you add to 100 milliliters of 0.5 molar sodium hydroxide if you wanted the final concentration to be 0.15 molar? Okay, so CI, VI, CF, VF. We want the final concentration to be 0.15 molar. The kitty cat. The initial volume is 100 milliliters, and then the initial concentration is 0.5 molar. Okay, so carefully read this question. How much water would you add? It didn't say what is the final volume. Before we can figure out how much water we would add, we have to figure out the final volume. So we're going to solve for the final volume. So CI VI over CF. So 0.5 molar times 100 milliliters divided by 0.15 molar. Units cancel out. Our final volume is So the correct number of significant figures, 333 milliliters. Now the question asked for how much water would we add. So the amount of water added would be the amount of water added would be the final volume minus the initial volume. So 333 milliliters minus 100 milliliters gives us 233 milliliters. So the answer to this question is 233 milliliters. And if that explanation wasn't completely clear to you, I'll draw you a picture at the bottom of page 14. You start off with 100 mils. To dilute it to the appropriate concentration, you add water. So now our new volume, or our final volume, this was VI, our final volume came out to be 333 milliliters. So this is the amount of water we added. 333 milliliters minus 100 milliliters, which is 233 milliliters. Okay. So hopefully you're getting the hang of these dilution problems. Number 5 is another one that asks you for how much water. So question, how much water must you add to 100 milliliters of orange juice concentrate if you want the final juice to be 20% the strength of the original? I don't see 3 numbers there. She's lying to us. All the information you have is there to solve this dilution problem. This is a dilution problem. Our initial concentration is set at 100%. We want our final concentration to be 20%. So I'm going to put a decimal there so you don't have to worry about sig figs. So it's 3 sig figs right here. Our initial volume is 100 milliliters. And just like with the last problem, we're going to have to solve for the final volume and then calculate how much water must be added. So VF is CI VI over CF. So 100% times 100 milliliters divided by 20%. Percents cancel, left in milliliters. We get 500 milliliters is our answer. The amount of water will be BF minus VI. So 500 minus 100, so it would be 400 milliliters of water. Alright, so on the next page, I have some dilution problems and I have some concentration problems. Now remember I said on the exam these are all going to be mixed together. So you have to be on the lookout. Is it a dilution problem or is it a concentration problem? So I want you to hit pause and work through problems 6 through 10. Alright, so numbers 6 and 7 are dilution problems. They don't ask for the amount of water that was added. Number 6 is just asking for the final volume. So 2 sig figs, your final volume is 0.15 liters. Number 7 is asking for the initial volume. It's also a dilution problem. The initial volume is 375 milliliters. Number 8 is not a dilution problem, it's a concentration problem. So your starting quantity is the number of moles given. Molarity is your conversion factor. So you convert moles to liters using your molarity, and then you convert liters to milliliters. So you end up with 5.3 milliliters. Number 9 is a concentration problem. It's a different looking concentration problem. The key is knowing that sulfate ion is SO4 2-. So the question asks, what is the concentration? It gives you the concentration and molarity. So molarity is moles of sulfate ion over liters. 1 liter. I need to convert this concentration to equivalents per liters and milliequivalents per liters. Really, all I need to do is convert moles to equivalents and then equivalents to milliequivalents. So remember moles and equivalents from way back when at the first part of Unit 5, 1 mole, 1 and mole always go together, and then the number of equivalents is determined by the ion charge. So it's 2. So 2 equivalents. So you have 0.050 equivalents in 1 liter. So that answers this part of the question. To convert equivalents to milliequivalents, you're just going to multiply by 1,000 or move the decimal 3 places to the right. So 3 places to the right would give you 50 milliequivalents per liter. The last problem is a concentration problem. So your starting quantity is this one. So 500 milliliters is the starting quantity. And 0.5% is the conversion factor. So you end up with 2.5 grams. So practice, practice, practice. Dilution and concentration problems are notorious for causing students a lot of grief in Unit 5. Work on the concentration lab, also work on your pink book, and work on your homework problems that pertain to these sections. The more you practice, the easier this will become. And remember that nothing is easy when you first attempt it, so keep persevering. Until next time.